Hello? Divya, can you hear me? Hello? I can't hear you. Hello? If there's a problem in the audio, you can write in the chat. Shall I start? Yes, I guess you can hear me. Can you write in the chat? In the Google Meet chat. Okay, fine. So it would have been good if you could like speak up. Otherwise, just try to communicate via this chat section. So this today will be week 3. Last week 2 was on Tuesday. If you can get the week 2 Tuesday 3 to 5, you can get the link from the weekly log sheet. I think you have access to the weekly log sheet, right?
Okay.
Yes. Yes, right. I guess that is yes. So what I'll do today, I'll try to go through the assignments that you have shared with me, and I will try to discuss those, how to solve them. Have you solved it already?
No, sir. I was busy with the lab work yet, so
Okay,
I didn't
fine.
get to
No, it's fine.
see.
We'll discuss, and I hope by the end of this session, it will be easier for you to solve them. I'll just discuss some. We might solve together, and and at the end, I'll try to go through some lectures. Have you gone through the lectures or not?
No, sir. I was occupied this weekend.
Okay,
I was
okay,
busy.
okay. That's fine. That's fine. So week 3, if you go through the lectures, you will find some interesting stuff there. I will try to touch some of them. So let's get started. I think if people join, they will be joining. Okay. So first question: what are the dimensions of kinematic viscosity? So do you remember what kinematic viscosity is?
Yes, sir.
And can you tell me? So what are the kinds of viscosity we have?
Dynamic viscosity, kinetic viscosity.
Dynamic viscosity and kinematic. So what is dynamic viscosity? What is dynamic viscosity? We write it with eta, right? And kinematic viscosity with nu, right? So what is the relation between them? Do you remember? If no, you can say no, no problem.
That.
Yes, you remember or not?
No, I don't.
Okay, fine. That's fine. If you don't know, that's fine. Don't be shy. Just say no. So dynamic viscosity is kinematic viscosity by rho. Rho is the density of the fluid. Now can you tell me what is the dimension of, so that they have asked the dimension of kinematic viscosity. So the question is, what is the dimension of this nu, right? Now can you tell me what is dimension of rho first? So to calculate the dimension, we have to know dimension of these two, right? So first let's start with rho. What is the dimension of rho? If you don't remember, it's fine. How do you calculate it? I don't remember what is the dimension of rho.
M into L raised minus 3. Mass, mass per volume. Mass by volume. So
Mass
M
by.
into L raised minus 3.
Okay, fine. And what is the dimension of eta? How you will get it?
M into viscosity, right?
Yes.
M into L raised to minus 1. T raised to minus 1.
How did you get it? Did you memorize it or what? No, you can.
Viscosity like force by dV by dz. F by that equation is
Okay,
pressure
okay.
by dV by
So
dz.
force by area dV by dz. Okay, let's try to calculate. And this proportionality is eta, right? So eta will be F by A dz dV, right? Correct me if I am wrong. Force is ml to the power minus 2
Uh,
L square L L T, correct?
Viscosity is pressure by shear rate.
Yes. So is it
F
that?
by A, it will be in denominator now. dz by, the gradient will be in denominator. dz by.
No, I have written dv dz, and here I have changed it to dz dv. Is it correct? So tell me this equation is correct or not?
Okay, yeah, that's
Okay,
right.
okay, okay. So what does it give you? L cancels. M L inverse to the power minus 1. Now you can calculate, right? Sorry. Now you can easily calculate what will be the. So just divide it. Something like L to the power minus uh, L square T to the power minus 1, right? The answer. I think this will be the correct answer. Okay. Fine, right? I did everything correctly, or did I make any mistake?
Previous slide can show.
So what we got is rho is ml to the power minus 3, and so if you divide eta by rho, if you divide these two, you what do you get? M L inverse t to the power minus 1 by m L to the power minus 3. So L square t to the power minus 1, right?
I thought I got.
Yes. Any doubt? Okay, thank you. So that's it. Okay, choose the correct size relation for cellular and subcellular structures. Do you have any idea about this? Like, is this correct? Virus is higher than bacteria, is higher than cell nucleus, higher than mitochondria.
Bacteria is bigger than virus.
Yes, bacteria is higher than virus. And also this cell nucleus and mitochondria. So this is not correct answer according to you. What will be the in the next one? So if you don't know, it's fine because you don't have to.
Oh, sir, is it option C? Is it option C?
C, plant cell, flu virus, lipid molecule. No, I think this one is greater. So if you go to the lectures, there has been this slide. This is very interesting. Just go through the lecture. I have taken this from here. So you see, lipid bilayers are pretty small than plant cells, right? Also, flu virus is so higher. So lipid, flu virus, plant cell. Lipid, flu virus, plant cell. Yes, this is correct. Also, option C is correct. Also, if you look at option B, you see this bacteria and mitochondria are almost same in the length scale, which is lower than RBC, which is shorter than RBC, and which is shorter than pollen. So this will be also correct, right?
Okay, sir.
Yeah. So in this question, two options are correct, right? Plant cell, so lipid bilayer, plant cell, and flu virus. Yes. So this is wrong by looking at, you can tell. So this is you should go through these lectures. You will get this, and he discusses about this in very good detail. Okay, so this question, if a ribosomal subunit is being purified from cytoplasmic extract of eukaryotic cells like HeLa cells, what is the expected velocity with which 40S subunit will settle? So there is one information here, 40S subunit will settle. The tube is being centrifuged with an acceleration of this times g, with g equals 9.8 meter per second. The answer for order of magnitude. So these are the three information have been stated. Now you tell me, do you know about this centrifugation?
Actually, that's in week 3 session, so I haven't gone through
Yes.
the lecture series yet. So.
Yes. It is in week 3, centrifugation. And if you go through centrifugation, like what do you think? What do you uh, can extract from this term centrifugation? Let me go. Yes. So I was anyway going to discuss centrifugation. So what do you think centrifugation could be? So one clue is centrifugal force. So you use centrifugal force to separate some. Hello, Prasad.
Hello, yes, sir.
Hi. So this is week 3. So can you introduce yourself? Like.
Well, sir, my name is Manish Prashant, and I'm a working professional. So I'm working on Java and UI.
Okay. So okay. So you work in a company or something? Hello. Hello. Can you hear me? What the hell?
Repeat. Yes, sir. So overall, these are the things like this.
I'm sorry. Hold on. My internet got some
Actually,
issue.
sir, last week I tried to join the call,
Hmm.
but there was some network issue. Because of that, I was not able to join. I replied in the mail. So today I thought like I will just try it again. So now I am able to
So
join.
last week, the last Saturday.
Yes, sir.
Okay, you tried to join. Okay. So there was another class on Tuesday, last Tuesday, because at the first week I couldn't take the class. Uh,
Okay.
so it is in the link. So no one joined. So it is a short. It was a short lecture, short session where I just discussed the. I just discussed week two assignments probably. You can go through it, and it happens in every Saturday. So I am Sahil, by the way. I'm a PhD. I'm doing my PhD in IIT Hyderabad in biophysics, simulation and modeling stuff. I do mostly simulation, not experiments, and I'll be so I'll tell you this session will be a discussion based session where I will go through some assignments or some problem that has been discussed in the main lecture. I wouldn't repeat much from the main lecture, but I would expect you guys to uh, have a discussion and try to answer some stuff. Okay.
Okay.
So you have to be you have to discuss and unmute yourself, and I will be asking questions, and just please respond. And one more thing, I'll request you, just please drop an email in this email so that I can communicate with you guys. Uh, After this session, you can drop an email here. Okay. So have you, Prasad? Have you gone through the lecture of week three?
Sorry, sir. It was last lecture. I was not able to join. That's what I was like not hoping that I will be able to join. But I will go through, sir. And because like working employee, so I have to Saturday, Sunday only these 2 days. So I will go through the recording, sir, and I will be
Okay,
ready with
okay,
my questions also. Yes.
okay. Fine, that's fine. See, you don't have to hesitate. Like if you have not gone through, it's fine. We'll be discussing it. Please go through it. Some assignments. So I guess you got those assignments.
Hmm. Okay.
I'll go through it, and please go through the main lectures, and yeah, that's it. And can I ask you, what is your training before working? What is the background you have, so that I can be
Sir,
sure to ask you the.
yes, sir. I will tell, sir. So actually, I'm completely from the like computer background. I have actually I'm not like a BTech. I have like a BCA, and after that I did the MSc, and after the MSc I did the job. So 2014 I have completed my MSc from Rajasthan University,
Okay.
and I have the networking experience also. I have like 1 year of the diploma, and
Okay.
now you can say after the 10 years, 2024 onwards, I started like my study again. So currently I'm pursuing the MTech, I told, from the Vinay Nagpur, and the stream is applied AI. Okay, so while doing that, I was looking like some other scope also because actually I'm a like full stack Java developer. Okay,
Okay.
so currently I'm holding a lead position, so lead one software engineer. The position is fine. So see the Java profile is fine, but actually I have more interested in the AI field. So that's what I was looking for something new. So I am current because I am pursuing the MTech. I was looking for some better scopes also. So I went through from the NPTEL this course, and I think you was only there, was given the introduction of the course, like what the course is around. So I got some interest. That's what I applied for this one, and now I'm going through this one.
No, I didn't understand. You went through the which course in NPTEL?
Not any of the course, sir. Actually, there was one demo video when means actually this course I selected from the SWAM portal, and from the SWAM portal, like a course content, everything, and one recording was there, which will tell about this course.
Oh,
So
so
when I went through,
okay,
yes,
Chaitanya sir's course. Okay.
yes, 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 sir,
I
correct,
see.
sir.
see,
Yes,
I
sir.
see.
So with that only I got some interest, so that's what I applied for this course.
Okay, okay, that's good. That's great. That's great. Yeah.
Okay,
So you are
thanks.
good at coding. We will be doing some coding towards the end of this
Yes, sir. I have
session.
like the Java anyhow completely I have, UI I have, and Python I have started also.
Yes, yes, yes. That will be great. So we can have some help from you also regarding the coding part of this.
Okay.
Okay, it is towards this end of this, like weeks 8, 7, 8, towards that. Okay. So we are
Okay.
discussing. So we have already discussed question 1 and 2. You should go through the week 1 and week 2. Then you can will be easily answer what is the dimension of kinematic viscosity. Okay, so you will know that what is dynamic viscosity and what is kinematic viscosity. It is discussed in, I guess, chapter 1.
Okay.
And it is an easy question. This next question is about the size of different biological entities and how big are they compared to each other. So this is also, sorry, this is also discussed in the main lectures. Next we are in the third question. um, so we are discussing what is centrifugation. So centrifugation
Uh,
is, yes,
Sir, if you don't mind, I have one small question actually. Okay.
yes, yes,
So it's like, sir, not the content of the course. It's like about the course. Uh, if you can help me to understand, like which part of like in the the physics is this course is touching, and how it will be helpful. So just a small few words on this, so that will be helpful for me to understand. Because while looking at, I know the like what you are teaching, so I understood, but I have some doubts. So if you can just tell me, because it's a one-to-one discussion you are doing, right? So that's what
yes.
I am also open for this question. Okay, so if you can just help me to understand like what actually this cellular biophysics is this for, and how this framework will be helpful.
Okay, okay.
Yes.
Okay. So what I can tell you from here is, so this course, the way it is designed, it covers a lot of stuff. Like it it revolves around cells and cellular biophysics, but he has covered a variety of stuff from very uh, entry level physics to entry level biology. It is not very complicated, but sometimes he goes a bit deep in physics, sometimes he goes a bit deep in biology. So the way it is designed is like it, anyone from any background, if they want to have some overall idea about the subject, they can have it from the course. But if, let's say you are doing a major in cellular biophysics, I would say this course may not be the best course. But for an entry level, like you just want to understand what is the whole thing is about, you will get a very good understanding uh, from these lectures. And after that, like let's say you want to go deep, but you don't want a starting point, this course is the starting point. After that you can go in different directions as you wish to. Now what you are asking, that how it is helpful, I don't know, like if you want what you want, that you have to filter it out from this course. It has a lot of stuff. Everything you might not need in whatever of region of your choice. Did I make sense? Or
Yes, sir. Got it, sir. Got it, sir.
so it's fine, like you can ask questions, and just okay. So that's the main part. So it will have a lot of things. Out of curiosity, you can go through all of them. You'll like it. I think you'll like it, because the way he teaches is really good. And then you have to get into, like if you want to go deep in different stuff, you can go from here. But this is a good entry level course. Okay. And
Okay.
so if you don't understand anything, like any kind of physics related stuff, you can ask me, whenever I'm going through, like, do you know what dimension is?
Yes, sir. But it needs revision for me because
Yeah,
these all
sure.
the terminologies are known for me only, but a bit revision also because it's a 10 years of the gap.
Mm-hmm. Sure, sure, sure.
Yes. But sir, I will cover it, sir, because in the Sun portal already all the recordings are there.
Mm-hmm.
So now because we have one-to-one interaction, so it's a very good. Like you are very interacting directly with the students. So I will go through the recording and probably like next week I will be ready with
No, no, it's
all
fine.
the
Don't
information.
feel pressure.
Yes.
Do it as you feel feel like. We'll have discussions. Okay.
Okay.
Sure. Divya, are you there? Still there?
Yes, sir.
Okay. Okay. Yeah. Fine. I was just making sure you are here or not left. So, so Divya, for you, sometimes I like I may go slow a bit because if Prasad is also here, or if someone else asks some questions, I may need to like for you these dimensions and all are very basic, but for someone else it might not be. So I will try to get a bit slow or more explanatory. So what we are discussing, what is this? There is this question number 3. So the question is, what is the expected velocity with which the 40th subunit will settle? So first question is, what is this 40s meaning? What is this 40s? First question 1 is this. Question 2 is acceleration.
Sir, the screen is not visible. The slides are not visible.
Slide is not visible.
Yes.
I can see, sir. I can see.
Can you try pinning, Divya? I think it's
Yeah,
unpinned.
I can see. I can see it now.
Okay, okay. So 10 to the power 5 times g, and g is 9.8 meter per second. Sorry. So the answers are provided in order of magnitude. So first of all, you tell me what is this acceleration? You have, I know Divya will have the concept of acceleration. I'm just asking Prasad, do you also have the concept of acceleration? Like know what acceleration is, right?
Yes, sir.
Yes. So it is the rate of change of velocity. So how fast one thing is going, and it is 40 s. S is called this Svedberg unit. So what is it? To know it, you have to go through week 3. I think lecture 2, where he discusses sedimentation and centrifugation. So I'll quickly give you some idea about what this sedimentation and centrifugation is. So let's say this is related to sometimes you need to count. Let's say you have blood. Okay. Now you go to the for blood test. What they do is they take your blood. Then after that, what they do? Any idea? Any of you have any idea? Have you done any blood test recently? Any of you?
Yes, sir.
Sir, they will put the blood in the slide, and actually I just went through the videos only, and they will match. They will put some enzyme into this, and they will wait like which color is it changing,
Okay.
and based on the color they will put the blood
Okay. So you are saying blood. This is blood group test, right? You are talking about. Have you? Okay, that's correct. And do you know what CBC is? Have any of your doctors given you CBC?
Red count. Yes.
Complete blood count. So this CBC, what they do is it gives you, if you look at your report, it gives you how many RBC you have, how much hemoglobin you have. So this process needs, let's say you want to count RBC. First thing what you have to do is you need to extract, like blood has a lot of things. It has RBCs, WBCs, plasmas, and everything roaming around in blood, and it is a fluid. So to to separate RBC, this sedimentation process is used. So what is sedimentation? It's pretty simple task. Pretty simple task. What is this? They take your blood and, sorry, so let's say this is a test tube, okay, and they put your blood in this here. They put your blood and everything inside in this thing, okay. Now they wait. Now what they do, they wait. So because this RBC is heavier than WBC and much heavier than the plasma, what happens is eventually this RBC settle down at the very bottom. Then there is plasma, and then there is white WBC, and after that there is plasma. This kind of phase separation happen due to what causes this phase separation? Yes,
Density of sediment according to the particles.
according to particle mass. So this happens because of gravity, nothing else. You just keep it, and because RBCs are higher, they settle down here. So this is sedimentation. And another concept is centrifugation, where they take it put it in a circular stuff like this, circular disc, and they rotate it with some angular velocity. And when they rotate it, because of centrifugal force, some parts get separated towards the outward side, just like in your washing machine. What happens in your washing machine? You put your clothes and rotate it. What happens? The darts go outward because of the centrifugal force. You have an idea about centrifugal force, both of you?
Yes, sir, centrifugal and centrifugal.
Yes. So this is the, like, if something is rotating, it feels a radially outward force, but that is centrifugal force. So these are techniques used to have this kind of blood test, and it's a very widely and very common things are used. So to answer Prasad's question earlier, so this is, you see, this is the kind of stuff he is teaching. So where this blood test and stuff, it's purely taken from a biological point of view, okay. Biology and medical purposes they use it, but what is the physics is involved, he is teaching that. So I'll give you an idea about here. So let's say how the physics is there. You can calculate some stuff from this Fedberg equation. We'll try to, he has already derived, you can go through it. I'll give you one idea. So let's say it is the RBCs are moving in a velocity v down, okay. So in this velocity you want to calculate this downward velocity, right? So how will you calculate it? Any idea? Divya, do you have any idea about this?
sir, I don't know about this.
Yes.
Sir, can you show the slide again?
Oh, okay, okay. Hold on, hold on. Share screen. So you want to calculate V down, okay? Now this has a, let's say, mm, okay. So first of all, let's say one particle you have which is going through a fluid, right? So what will be its effective mass? What do you mean? What do I mean by effective mass? Let's say its mass is m, mass of the particle. So what is the effective mass if it is going through a fluid media? Why I am saying there is an effective mass? Any idea?
Because there are some dissipative forces. So
What forces?
the bind force is the viscous force is the viscous
Viscous
force
force,
acts effective mass will be
viscous force, buoyancy, all of this, right? So can I write
gravity.
this m minus v by rho? V is the volume, rho is the density of the fluid. Hmm? Is this correct? This is Archimedes principle. Prasad, do you remember Archimedes principle?
Yes, sir.
Can you tell me? The spelling might be wrong.
Sir, not able to recall. I remember, but okay. Actually, this is related to like one small experiment. What I remember, just I'm telling. So maybe I
Sure,
would be
sure,
wrong.
sure.
Okay.
Definitely.
So there will be the fluid and some mass if you are putting. So some water will be displaced.
Yes.
So there is a relation between the mass what we are putting and the water which is displaced. So actually that principles only like we are referring as an Archimedes.
Yes, yes, yes. So what Archimedes said that if you, let's say, put some object in a fluid, so it will displace some amount of water or the some amount of that fluid. So the amount of fluid that is displaced by an object is equal to the volume of that object. Like it's the same volume. So this, let's say, when you put something in a fluid, it has its weight which is equals mg, and it has a buoyant force because of this displaced fluid, which is equal to this same volume of this force. Now how do you relate volume and mass? How do you relate volume and mass? Answer, anyone?
Density is equal to mass.
Yes. So mass is it is equal to v by rho, right? Or what did you say? Density equals m by v. Divya.
Yes, sir.
Okay, so mass becomes rho v. So let's say, so how much force it will feel due to this upward force by the fluid. So this mass times g. So if you compare it, mg minus this rho v g. Okay, so this will be rho v. So you can say like m minus rho v times g. This is the force felt by that object. Now I can imagine there is an effective mass m prime, and if I write m prime times g is the effective force, I can equate these two, right? So that's how m prime becomes m times 1 minus rho v by m. So this is the effective mass. Did you understand this? First Divya
Yes, sir.
and then Prasad. Did you understand this calculation?
Yes, sir. Very sir.
Okay, nice. So this is the effective mass if a particle is in. Okay, there is another person. Hi, Dharika. Hello. Can you hear me? Okay, so this is an effective mass felt by an object that is in the fluid. Now let's say if
Sir, this equation is independent of gravity. Like, will it be same like if the calculation is in Earth or in the Moon? Because there is no component gravity, right? Here.
yes, it cancelled out in both sides. So I'm just saying this is the effective mass. Now if you
Okay.
talk about force, then you have to multiply it with gravity. That's how you know the force.
Okay.
We'll come to it pretty soon. So what happens is, let's say if now there is this Stokes equation or Stokes law. I know Divya knows the Stokes law. Prasad, do you know the Stokes law? Stokes law,
No, sir.
if a
No, sir.
particle is moving in a fluid of density eta, no sorry, viscosity eta, then it feels a force because of this viscous force, which is 6 pi eta rv. Okay, so what is this 6 pi coming from? That it is a different question. R is the radius of the particle, and v is the velocity of the particle, and eta is the viscosity. Now I can write F is proportional to, let's say R is constant, we want to calculate this V. So if we can write some constant, let's say gamma times V, right? Gamma times V. Fine. Any objection?
No, sir.
No, right? Now this force I can relate to this m prime via m prime times g. That becomes gamma times v. So this v becomes m prime times g by gamma, right? So this is the v down. Now there is this very famous equation from Einstein, Stokes equation, which connects this gamma to the temperature of the system. Excuse me for a minute. हेलो, हाँ मैं 5 बजे के बाद आता हूँ. 5 बजे आता हूँ. 5 बजे. 5 बजे आता हूँ.
सर अभी आपका जो भी ऑर्डर है सर मेरे पास 1 घंटा वेट करना सर. यहाँ माइटी में रखूँ, ले लेते हैं.
ठीक है, मैं तुम्हें ठीक. हाँ, yes. So I will request you all to go through this Stokes-Einstein relation, which connects these two. This gamma, first of all, this gamma came from this 6 pi eta, like in fluid, but you can connect it to the temperature of the system, which is d by kBt. kBt T is the temperature and d is the diffusion coefficient.
Sir, I have one small question, sir.
Yes, please.
Sir, here I can see one terminology is diffusion. Actually, what is this diffusion means?
Sorry, I wrote it the opposite way. kBt by d. Okay. Yeah, I'll come to your question. Hold on a minute. So let's say d is a constant. Okay. D is a constant for now. Now if you put it down, put it back to this part, what you get? V down equals m prime g d by kt. This relation is called Svedberg equation. Okay. So this relation gives you the downward velocity of any particle that is suspended in a fluid. Now the question is, from this relation you can actually calculate, you can get this m prime t and d values for RBC, for plasma, and you can see this V down value which is higher or which is lower. Now coming to your question, what is this d? So this is called, okay, so I didn't want to get into too details about this, but this d is called diffusion coefficient. So what do I mean by diffusion? So diffusion is, let's say you are in a room. Okay. Now you have some let's say you have put a spray perfume at a corner of the room. So what happens there? Eventually, and you are waiting, what happens? Anyone?
Sir, it should be spread all among the room.
Yes.
But wherever we are starting that spread, right? So there the intensity of the smell will be high, and other places it could be less.
And eventually what happens? It spreads out, right? It spreads all over the room. Yes, Dharika, you are correct. So Dharika, since you are replying, so can you just briefly tell me about your background and what are the trainings you have? Like you can write in the chat or unmute yourself, anything, so that I have an idea how much to explain and how much not to explain. Okay, so what where I so diffusion, yes, so this process is called diffusion. So from particles growing from one higher concentration to lower concentration, that is called the diffusion. So you can associate an equation to this equation. What is the equation? Let's say C stands for concentration of something. Let's say something means in this case it is the concentration of the perfume or let's say you have some this agarbatti let's say you have put it there, so the concentration of that thing. Now this C will be a function of position and time, right? You understand this position and time thing?
Yes, sir.
Yes. So it will be at some position and at some time it will have a value. Let's say you at some x it will have a value. I wrote x vector. That means it's not 1D. It can be 2D, 3D, anything. Okay. So in your room it will be 2D, 3D. In this paper it will be 2D, and so on. So what happens is you can write this relation, which is change of C with respect to time is proportional to the second derivative of C with respect to position. Okay. So what this tells you, change, like the way this C is diffusing is, it's like an let's say an acceleration happening in space, and these two are proportional. Okay. And this proportionality constant is d x square. So this d is the diffusion constant. From here this d comes. Okay.
Okay, sir.
So I know it might not be totally clear yet, so you have to go through some stuff. If you are interested, you can look up diffusion or heat diffusion, everything. You will have some better clarity about this. So this d comes from this equation, diffusion coefficient it's called. And Einstein what did this, it related this d and the temperature of the system to this friction coefficient that was in this Stokes law regime. And if you put everything back, you get this Swedberg equation, which is this thing. Now you tell me this V down, now you have this V down, and you tell me what is the dimension of this V down by G. Can you first let's ask. Okay, Divya is not here. Dharika, do you know what dimension is and how to calculate dimensions? So okay, fine. Prasad, you tell me what is the definition of G. What is G? This G.
G, sir, are you referring that gravity
This is
constant?
gravity, yes. So it's called, yes. So better answer will be gravitational acceleration.
Normally 9.8 meters.
9.8 meter per
Meter per
second.
second.
So this is G is also, sorry. So this is called gravitational acceleration. Like let's say if a object is falling through vacuum or air with only via gravity, this is the acceleration it will have. It is not a velocity, it's the acceleration. So it has an unit of meter per second square. Now you tell me what is this unit of V down. What V down means, essentially it's a velocity. And what is unit of velocity? What is the unit of speed? Meter. So okay, so Dharika, meter is not correct, because meter is the unit of length.
Sir, we have to compare always, like meter per second or kilometer per second. So then it will give the actual speed.
Yes, so speed is kilometer per hour. Let's say your car or something. What is the speed? Kilometer per hour, right? kmph. Yes, Dharika, what? So you are answering about So whatever kilometer and meter, these are only length or or the distance. Now if you want to talk about velocity or speed, you have to tell me how much distance something is covering in a particular second or particular time. Yes, meter per second, correct. So kilometer per hour, meter per second, centimeter per second. So these are the units of velocity. Now let's say meter per second. Now what comes down? V down by G. V down is meter per second and G is meter per second square, right? So it essentially becomes second. So this V down by G is second. So this is how we call it. Is not it is that it is not actually it is the unit of V down by G will be second and the dimension will be T. T means equivalent to the dimension of time. So this for blood, this V down by G is called S. So S is related to 10 to the power minus 13 second, and this capital S is called Svedberg's unit. You understood this calculation?
Yes, sir.
Yes. Thank you. So now let's go back to that question again. Question number 3. Now this 40S subunit, this means capital S means 40 times 10 to the minus 13 second. That is the time V down by G. Now it has some acceleration of 10 to the power 5 G. So how to reach this kind of acceleration? So this is centrifugation. When you rotate it, and when you rotate it, you get accelerated, and this acceleration of rotation is calculated by r square omega. So any idea about what I have written and how what is this? If not, then it's fine, just tell me, then I will have to give you some explanation about this r square omega thing. What is omega?
Sir. Sir, then you can please a bit explain, sir.
Yes sir, Prasad, couldn't hear you.
Sir, I'm saying that then you can a bit like just explain, sir.
Yeah, I'll just give you some hints, okay?
Okay.
How to I guess so. Divya is not here, Darika is here. Don't hesitate. If you don't know, just say don't know. It's not, I'm not gonna judge or anything. It's a discussion, okay? So I also don't know a lot of things here. I'm also learning with you guys only. I'm going through these lectures every week and coming to have a discussion with you guys, okay? So omega is called angular velocity. So let's say you have a rope, okay, and you attached a let's say a ball or any mass at the end of it, and you take it and rotate it. Like you can see my screen, right? Like you can see me, right?
Yes, sir.
My video. So let's say I don't have a good here. Let's say this is a charger and this is my mass and this is it, right? So I am rotating it like this, or I am rotating it like this, okay? So when I am rotating it, what is the difference between this rotating stuff and let's say it was moving like this? What is the difference between these two? Basic difference.
Sir, rotation is under one boundary, and if something is going forward like that is a scalar, so then there is no boundary that I can understand.
No boundary. Okay. You are not exactly accurate, but you are in a good direction. So what you are saying, there is no boundary means if it is going like this, let's say it's going like this, it will go on and on forever, right? Newton's law.
Yes.
Now,
This is straight. Yes.
yes, now if you attach something to this and rotate it, that's this length is making it fixed. It can't go away, right?
Yes, sir.
It so if I can change it, right? Change this length.
Yes, sir.
So this length is your arc. This arc. Okay.
Okay, sir.
Now let's say I'm rotating it like this. Now what you will see, this, let's say it starts at this point and does a full circle and comes back in here, right? This is what
Yes,
it
sir.
is doing.
So something like pendulum, like it's a fixed.
Yes, it's a pendulum. If it is pendulum, it's like this. There is no rotational radius involved.
Yes, sir.
And this R I am talking about, sorry, this, if I am rotating it like this, then this length is equal to the R. Now if I am rotating it like this, imagine there is a circle it is making on this plane, right?
Okay, sir.
So this R will be the radius of this circle that is making.
Okay.
First thing.
Okay, sir.
Okay,
Okay.
that is clear. Now you tell me, have you ever come across this term called RPM?
Yes, sir. Rotation per minute. Per
Exactly.
motor. Yes.
Exactly. So Darika, do you know what RPM is? Okay, you can write in the chat also. Fine. I'll just assume you don't know. So RPM is rotations per minute or revolutions per minute. So what does it mean? So you see, let's say it is rotating like this. Okay. Now let's say it started here, covers one full circle, comes back here. Let's say it takes 1 second to do this, and it is doing this, and you are measuring how much time it's taking. So this is one full rotation. So you are calculating how much time it took to do this full rotation. Okay. So this is called RPM, rotations per minute. So how many rotations? Let's say 1, 2, 3, 4, 5, and then 1 second happened. That means 5 rotations in 1 second. That is 5 RPS. 5 rotations per second. Now you can convert it to RPM. So this RPM or RPS is the angular velocity of this rotating object. Okay.
Okay.
So when we talk about RPM in motors or in any cars, you will see in cars also. So this is the RPS. So this is the angular velocity. So this relation r square omega gives you, this is called angular acceleration, r square omega. Okay. So this angular acceleration is converted in terms of g. So how much more you have than g? Let's say you have omega is, let's say 100 rpm, okay, and r is 10 meter. So can you calculate a? So r square omega, right? So 10 square times 100 square rpm square. Now you get something like 100 10 to the power 4, 10 to the power 6 in rpm meter square rpm square. No, sorry. Omega is not squared, right? So 10 to the power 4 meter square rpm, correct? Now you can convert this to meter per second, right? If you convert this to meter per second square, if you convert this to meter per second square and divide this whole thing by g, you will know how big this acceleration in terms of g, how much faster or how much slower this thing is rotating in terms of g, okay, than g. So this is how these things are expressed. So what this question is saying is the tube is rotating at 10 to the power 5 g, okay.
Okay, sir.
And now we have to calculate expected velocity. So all information I have given to you. So this will be the formula used for expected velocity. So see, you remember capital S had the time, and acceleration has mm, velocity per time. Now if you multiply S times A, you get this velocity dimension, okay. So if you multiply these two, you will get the answer, and you have to calculate it this way. Like it has given you the acceleration, it has given you the how much S value Svedberg constant is there, and you have to calculate this velocity, expected velocity, okay. I think you will be able to calculate it now, right?
Yes, sir.
Okay, fine. Okay, so this was question number 3. You understood, right? I hope you understood. Darika is not saying anything. One thing like to tell Darika that please drop me an email in this email, okay? Please drop me an email, because if there is any change of timing, I'll directly mail you. Actually, yeah. So please do that. Like if any changes are happening on the timing, sometimes like usually it will be on Saturday, but if something comes up, it I may have to change like 1 week. Like this week one I couldn't take, so I took it on Tuesday. At the last this week Tuesday, might be next week. So what are your plan? Like, can you tell me? Are you available on next week? Because I might not be available. So next week Tuesday, are you available?
Tuesday, sir, at what time?
3 to 5, let's say.
3 to 5. Okay. Sir, actually, that is a working time for me.
Okay.
But if it's scheduled already, then I will try to shift my other work and will be available.
Okay. Fine. Like, okay. So I'm not fixing anything yet, but probably I wouldn't be able to take the class on next Saturday, which is, let's say, which is 17th, right? Yeah. So if I couldn't take it, there's a 20th I might take. So I'll inform you. So to get this information, you have to email me, because I am not in the discussion forum. Okay.
Okay, sir.
So please drop me an email. So question 3 is done. Question 4. Okay. Reynolds number. Do you know what Reynolds number is? Prasad, you don't know or not?
I don't know, sir. I'm just checking.
Fine, that's fine. Darika, you know what Reynolds number is? 3 to 5 working time. Okay. Okay, you are also some working personnel, I guess. Then okay, if not, we can like shift it to Sunday maybe. Sunday also. Okay, so what I'll do is, I'll collect your emails and open a mail thread. You reply there. Okay.
And sir, can I just in the chat I can mention my email ID? Yeah, sorry.
Okay, just okay, okay. If you write it, I have to note it down somewhere. Okay, the both of you please write it.
I just message.
Uh, Darika, can you write also? Okay. So I will write whatever is happening. You reply there. That will be great. Okay, so Reynolds number I'll tell you. I'll try to keep it simpler. So let's say you have a fluid and something is swimming. Okay, in that fluid. Let's say you will have a fluid like this, and some fish is swimming. Let's say this is your fish is swimming, and another human being is also swimming there. Okay, so let's say this is a human being. So for those two, like not together, let's say fish is swimming and in another fluid the human is swimming. So for these two, what will be the difference? Like, tell me from your intuition, what will be the difference in flow?
Sir, sorry, but can you please repeat, sir,
So
one more time?
you have a fluid, you have water, fish is
Okay.
swimming, and another you have another pond. Let's say there is a human swimming. So what will be the flow? Difference in flow in both the cases. Difference in fluid. What do you expect?
So the first important thing is the structure of both. Because fish is already designed for swimming, and human is not designed for swimming, so they has to put a more effort. Like they are trying to use their hand
Yes.
to cross the water and to go forward.
Okay. Correct. So what will happen to the water? Like how the water will move? In simple terms, not asking very technical thing. Like very simple. In which case, let's ask this question. In which case the water will be more juggling or more uh, peaceful. Let's put it this way.
Sir, what my understanding, if we are trying to swim like in the surface of the water, then more juggling. And but if we are swimming inside the water, like inside the sea, right? So then there is some difference because then we have to move the body accordingly so that we can go forward. Means we are pushing ourselves towards upward direction. But the same way the fish also do. Fish will never swim over the layer of the water. They will always go inside the water. So their
Correct.
swimming will be equal once we are swimming inside the water. But as a human, we can swim in the layer of the water also. Then more juggling will be there. We have to use our hand, legs, everything. And but if you are going inside the layer of the water, then no more juggling, then less juggling, and we have to push ourselves forward.
Yes, yes. So Darika is saying move backwards. That is also correct. All of them are whatever you are saying is correct. But I am not asking that. So I'm not able to. So I'm saying, let's say in which case there will be more waves in the water, more disturbance in the water.
If we are going the anti direction of the flow of the water, then there will be more juggling. And if you are going from
No, 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 no. Let's say
means
both
swimming
the
in the
cases.
like flow of the water itself, then any of the less.
No, let's a pond. You have a pond. There is no flowing. Like there is
Okay.
no upstream downstream case. Simple pond is there. A tiny fish is moving, and you are trying to swim. Which one will create more disturbance in the water?
Definitely humans.
Human, exactly. One thing. let's say now, let's say you now let's say there is no fish, it's just you. You are trying to swim, but your speed is slow, and in another time you are swimming very quickly. In which of these cases will have more disturbance in the water?
I believe, sir, when we are swimming quickly, then less disturbance in the would be there in the water. And if we are more like trying to see in my what I can see, so we are more trying to fight with the water, then our speed will be less.
Okay, so slow human, fast human, right? So this, like, I'm ticking for disturbance, right? Now tell me, human, human, one is water, another is honey. They are both same human being. One is moving in the water and one is moving in the honey. Which one will create more disturbance? Honey, or let's say um, grease, or
Yeah, honey, grease, I got it, sir. Or maybe the like muddy sand, like we can say,
huh.
right? So anyhow, sir, water will give a less disturbance, and which is like these things, another things, right? It will give a more disturbance.
No, 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 okay. You were saying water will be less disturbed.
Yes, sir.
Okay.
Because we are trying to swim, right?
Hmm.
So swimming is possible only in water. Other like because it's a dense, right? Density will be more. So there are like we cannot swim. Maybe we will try to walk through. That will be possible. But if you are trying to swim, right? So then we have to put a more and more
More
effort.
effort, yes. So it's
Yes.
hard to disturb honey than water, right?
Yes, sir.
Yeah, that's what I'm trying to understand. Like, okay,
Yes, sir.
fine. So let's say I defined, I combine all of this and um, define a quantity which is looks like this. Okay, so rho is the density of the fluid. U is the velocity of the swimmer. L is the length. Eta is the viscosity of the swimmer. Okay. Now you tell me what will be. Let's say this is a this is a quantity called A. Okay. Now I'll give you one hint of what is eta. Eta is the unit. Okay, tell me units now. Okay, since this thing, this is called dimensional analysis, we'll do the dimensional analysis. Since you are not very familiar with dimensional analysis, uh, you can think of it like units. Now you tell me what is the unit of, remember, rho u l by eta, right? So tell me the unit of rho, density. Have you
Uh,
heard this? Kg per
yeah,
meter cube. Yes.
yes, yes, sir. kg.
Yes. Kg per meter cube or gram per cm cube, centimeter cube. Gram per cc, you might have heard it. Gram per cc. We already do meter per second square, right?
Yes, sir.
L is meter, and eta, I'll tell you, it's force by dv by z, like velocity by length. Sorry, not force. Force by area, which is equals force by area, length by volume. Okay, we have already discussed it at the very beginning of this class. So viscosity is m n inverse e to the power minus 1 m m L inverse divided by minus 1. This is gram centimeter inverse second inverse. Okay, now let's calculate this quantity rho u L by eta. So gram per cm cube. Okay, let's say write is centimeter. Rho u, what is u? Centimeter second to the power minus 2. Sorry, centimeter per second. Okay, L is centimeter and eta is gram centimeter inverse. I am putting it there. Second inverse I am putting it here. You understood this or not? Yes or no? I want.
Yes, sir.
Please answer.
Yes, sir. Yes, sir.
Okay. Dharika, I hope you understood this. I'll just assume. Sorry.
Sir, your screen sharing is off.
Just so this quantity what I have written right now is called the Reynolds number. Okay, so it, if you see here, everything cancels out. Gram, centimeter cube, second. So it does not have any unit. Or dimension. It's just a number. Now you see, it is proportional to length and velocity and inversely proportional to the viscosity, right? You see this proportionality and stuff, you understand this, right?
Yes, sir.
Now you see, if L is high or U is high, this Reynolds number is high, right? If U is high, L is high, RE will be high. But if eta is high, RE will be low, right?
Yes, sir. Yes, sir.
So this is the thing I was talking about when I was asking these questions. So all of these tick marks are not, you can quantify using Reynolds number. So if Reynolds number is high, then you know there is more disturbance that is getting created in the water, right?
Okay, sir.
And if Reynolds number is low, then it is less disturbance. So this Reynolds number is very important in fluid dynamics. Whoever does this fluid dynamics and stuff, they talk about Reynolds number. Low Reynolds number and fluid and high Reynolds number fluid. Like if Reynolds number is very high, then there is this concept called turbulence. Have you heard this turbulence? What term turbulence?
Yes, sir.
Yes, I will not get into this stuff. If Reynolds number is high, then the fluid is called turbulent flow, and if it is low, very significantly low, then it is called streamline flow.
Sir, that is mostly like when the dam is there, right? So where the pressure is also included in the fluid, means for the fluid. So then this terminology will be used always, the turbulence.
What terminology?
This turbulence terminology, what I'm saying, right? So in the like water, if there is another means body like pressure will be improved, right? So then this will produce a turbulence.
Yes.
Which is the main concept behind that dialogue.
Yes.
Yes, sir.
Correct. So what I am saying is, let's say you are swimming in water, you are creating turbulence. But a very tiny object is swimming in water in pond, it's not creating turbulence in the fluid, in the water.
Okay.
So now you know this Reynolds number definition. Now you can solve this question 4. So what we are doing is week 3 assignment we are discussing. Okay, so this is the assignment was given, you might have to submit it. Now let's say what is given. fish of 2 centimeter length. So you know this L, 2 centimeter. Water and honey. So you need this rho and eta of water, which is not given because you just can look it up anywhere. And swimming speed is given 1 centimeter per second. This U is given. These 4 quantity you have to look it up, and if you put back, you will know the answer. Okay, fine till now.
Yes, yes.
Okay, and next question: what factors do not make blood a non-Newtonian fluid? So there are lots of information in this question. First, blood a non-Newtonian fluid. So we have had a pretty good discussion in the first week 1, about Newtonian and non-Newtonian fluid. Okay, Newtonian
Yes.
and non-Newtonian fluid. Any idea, Prasad?
Yes, sir. This terminology is
You don't know, right? It's fine. It's not expected. Like you are from a different part of this kind of stuff. So I would not get into very much details about Newtonian and non-Newtonian fluid today, because in week 1 I have discussed it in pretty better description, but I'll give you some idea about it. So Newtonian fluid is the kind of fluid which does not change. Okay, let me write down. It does not change its viscosity based on flow, that is shear rate. So what does it mean? Okay, tell me one thing. What is the difference between a toothpaste and water?
Sir, the first thing is the composition. Water just molecules H2O, and toothpaste part of the H2O, like it has multiple things
Multiple components.
included.
Okay. So you
Yes,
tell me,
multiple
is
components.
toothpaste a fluid?
It's like some, I can categorize that is a fourth element, and normally what we are saying, right? So it's like a solid, liquid, and gas. A part of that, like something like the jelly. So that type of the category, maybe we can say.
Gel does not belong to solid, liquid, gas category, right?
Yes, sir. Yes.
So okay, when you are trying to take a toothpaste out of your tube, like if you press it, it kind of flows, right?
Yes, sir.
But if you don't press it, it does not flow, right?
Yeah. Yes, sir.
So it feels like whenever you are pressing it, it flows. It behaves like a fluid, right?
Okay, sir. Yeah. So if we are not applying any external effort, so that is like a solid. It will be there as it is.
Yes.
And if once we are applying, so it will behave like a liquid property.
Correct. So you see there is something interesting going on in there. Not like does it happen with water? No, right?
No,
Yes.
it will not happen.
Yes. So do you know about cornstarch?
Cornstarch. Yes,
I'll
sir.
show you a video. Okay. Can you see my other screen?
Yes, I can see.
Corn. Look at this video. Can you see the video?
Yes, sir, I got it, sir. I saw that video.
there was this good video where
Once everything's perfectly organized,
so in the
I'll start
lectures
working
they
on
have
my
shown a good
thesis.
video about fluid. I try to get it. So look at the fluid they are jumping on. See anything?
Yes.
Okay, these are not a good video. You can see my screen, right?
Yes, sir, I can see, sir.
Yes, sir. Hello.
Am I audible? I'm speaking, sir. I can see your video.
But you should be excited. In fact, biology is the most complex form that I think nature. General constitutive model for a dense fine
I
particle
couldn't hear
suspension
you.
validating many geometries.
I hope you are saying this. Hello.
Yes, sir, I can see you, sir. I can hear
Okay.
you.
Sorry. I muted myself. Sorry. My. So look at this video.
Oh, okay.
Look at this.
This material whose
So you should go through. This is the part of the
and
lecture
I see a
actually.
glass of water. It's not a ground
Yes,
level.
sir. Actually, I
But
once you shown the video
with
in the YouTube, right?
water
So then I understood.
material.
I saw this
Can you
material.
YouTube link?
Even that is something like a mystery for me, like how it works.
So what is
Sir, hope
happening?
hope I am audible, sir.
You are audible. What is happening there? Can you tell me?
Sir, see,
Like
normally
the
I can
observation.
compare.
I'm not asking about the mechanics or how. What is the observation there?
Sir, observation is like there is a something like all the material
Hmm?
is combining a force and like behaving a different way. What I can say. But
What is the
if
different way?
we
I'm
are
asking
breaking
about.
those materials, then the behavior will change.
Yes, but in the case of cornstarch, what is happening exactly? Like observation. I'm not asking. Don't have to tell me any mechanics, like force and all. Just what is happening. That's why I'm trying to find out the good video there. Uh, it did show. No, here it is. You see? Yes, this one. You see, this is the cornstarch. Okay, so they are picking it up from the by a spoon, and suddenly it behaves like it solidifies. Now they are putting hand slowly. Not it's like a fluid, and the moment they punch it, it behaves like a solid. Anything? Notice anything?
Sir, once we are dealing with its surface, then it shows as an hardness. But once we are going deep down, then that hardness will no more will be there.
Ah,
So
so
surface is behaving a different way, and
no,
that material is behaving different way.
no. Your observations are correct, but that is not what is happening. What happens
Okay.
is, if you are punching it, then it is behaving like a solid, and if you are slowly putting your hands inside it, it is behaving like a fluid. So it
Okay, so
depends on
force
how
matters.
fast you try to disturb the system.
Okay, sir.
So if you are doing it fast, it behaves like a solid. If you are doing it slow, it behaves like a fluid. Like opposite to toothpaste. What happens in toothpaste? If you do it fast, it flows faster, behaves like a fluid. But if you do it slowly, it behaves like a solid. It's the opposite behavior of toothpaste.
Okay,
So
sir.
these two are called, one is shear thinning. So these are non-Newtonian fluid. Okay. One is shear thickening. Shear thinning is, if you want to, shearing means the applying disturbance here. So if you want to shear thin it, like shear thinning means if you do it faster, it becomes thinner. Thinner means more less viscous. so that is blood. And if you do shear thickening, so that means if you are putting force faster force, faster shear, then it behaves like a more like a solid. So this is not a Newtonian fluid's behavior. Newtonian fluid does not change like this depending on how fast you are disturbing it. Okay, so
Okay,
this
sir.
much I can tell you. So you got the idea of what is happening there, like
Yes, yes, I
observation
got
is
it.
clear, right? And what is happening inside, deep inside, that is a, it's a different genre of physics. Okay, I have I have discussed a little more than this today. What I have told you in lecture one, week one of my series, and in the lectures also he has discussed. So same way our blood. So we are talking about cellular biophysics. So in biology, our blood is a non-Newtonian fluid, and how why it is non-Newtonian fluid, you will get to know if you watch like week 3 lectures. Okay,
Okay.
it is he has discussed it, so I am not going to discuss it to encourage you to watch the actual lectures. Now the question 6 is, I have already told you about the Stokes law. So the question you did, what is the drag force acting on an E. coli bacteria swimming at this speed given the viscosity of the fluid in which the bacteria means it 1 centipoise in water. So this is also, it's like, I think this is week 1 lecture. If drag is 6 pi eta rv, so eta is the viscosity, r is the size or radius of the particle that is going, v is the velocity. Now everything is given, you see what is the velocity they are given, v is given, swimming speed is given, no sorry, viscosity is given. Only thing you have to know that what is the r of E. coli, E. coli size of E. coli. If you know this, then you can calculate this drag force. Now you can ask me how I am writing this 6 pi eta rv. That is, there is no proof from the first principles like of this. This is Stokes law. It's more of a empirical law, experimentally observed phenomena, and could make it like you do some experiment, you put some balls in a long vertical, or let's say in any direction, you put something from inside a fluid and observe how fast it is going, how, like what is the effect of size, etc, etc, what is the effect of viscosity, and you come up with a observational equation. Okay, so there are
This all you explained, sir. You already explained Stokes law.
okay, so there, whatever, there is no definite proof of this. There are some, there is this equation called Navier-Stokes equation. Sometimes I'll not tell anything about this, but there is one way where you can reach this drag force from Navier-Stokes equation, that's it. But from this equation, if you put everything, you will get what is the result. Only thing you have to find out, that is size of E. coli bacteria. You will find it out in the lectures also, or you can Google it easily. Fine.
Yes, sir.
Okay, that is the last thing I was discussing. Sedimentation. Another question I want to ask you. I'll just ask it and leave it upon you. So let's say when this diffusion is happening, every particle, every molecule in this perfume, or say anything, have a so they're trying to move in a direction, right? Let's say they're trying to move in a direction, right? Now
Yes.
there are full of particles, right? Now one particle is moving, let's say it hits another and it changes its direction, and again there was another particle here, it hits again, changes its direction. So what will be the effective feel of this thing? Like, will they be move anywhere? Let's say you
Sir, always it will move from a high concentration area to the low concentration area. So until it will be the entire area will be in a balanced, the same layer, so it will move always. And if it's in balance, then it will stop.
Okay. So why you are saying it will move from high concentration to low concentration?
This is observation, sir. Like whenever like we already have, we are spreading the some like something in our home, right?
Yeah,
Like to
yeah.
remove the mosquitoes or things, it
Observationally,
will spread.
observationally, you are correct. What I'm saying that let's have to try to have a more deeper understanding if you want to have. So, what essentially this concentration um, uh, peak concentration is doing? There are molecules, right? So,
Okay.
high concentration here means there are a lot more molecules in this region than in this region, right?
Okay.
Any question here?
Sir, I think that is a property of that state of that matter, like the solid, liquid, and gas, all are having their own property. So once, see, inside the bottle, it will be in the liquid state, but once will spray, right? So it will dissolve and it will become a gas. Then it will become a gas. So it will try to assume the gas property, and gas, that is the property of the gas, like it will always move towards like the high concentration to the low concentration. Maybe that would be the reason.
Okay. Okay. So yes, that is also correct. So scientists have tried to understand. Okay. Sorry. Every time so scientists have tried to understand it in more
Scientific way, yes, sir.
scientific means like in terms of how movement of molecules. Okay. So I'll just quickly tell you in terms
If
of
this question is giving another question, sir, then how the diffusion will happen in the empty space, where like even there is no molecules. In like in the earth, we are talking about the, because it already has the air, so then the diffusion is happening. But some, because I know in the space related to the force, if something is stopped, it will always stop. If something is pushed, so it will go in the direction always, because there is nothing to change its force, right? It always
yes,
move towards.
yes,
Then the same how the diffusion will work over there. Like that is a force property, but now other properties like some diffusion, gas, some smell, how these are behaving in the space.
yeah, that is what I'm trying to say. So every molecule, like let's say you have uh, spread, like are you asking about vacuum or something?
Yes, sir. Space means a vacuum only. That's
Okay.
what I'm telling, sir.
Okay. So if it has energy, it can move, right?
Yes.
A particle. Yes, that is the thing, right? Like if it has energy, it will move in any direction. There will be no bias of direction.
Yes, that is correct. And once it will have the obstacle based on like its condition, it will change, because energy has the property to change itself.
Yes, yes, yes. It will dissipate energy and it will stop. At some point, it will stop.
Okay. Okay.
Right?
Okay.
It will radiate energy. As heat in vacuum in space. You are saying. I'm not saying that in space. Let's say in air only. Okay.
Okay.
Air you have
Okay.
sprayed some perfume. Now this perfume has a different kinds of molecule, right? Let's say these are the perfume molecules. So it it is, unless it is at absolute zero temperature, it will have some energy, right?
Yes, correct.
Now if it has energy, it has velocity.
Yes, sir, that is also correct. Yes.
Yes, so velocity,
Yes.
it is having, if it is have velocity, it will try to move in a particular direction.
Yes, sir, correct.
Now the moment it tries to move in a direction, let's say this one, let's zoom in here, and let's say this guy wants to move this direction, but it hits this one, so it moves in another direction, right?
Yes, sir, correct.
And
Yes.
it comes here, it hits this one, it goes another direction. So
Okay.
everyone is hitting everyone. So there is no particular direction this hitting is happening. The particles can move because any like any direction it gets try to go, it gets hit by another and it changes its direction. Let's say there was only one particle, it was moving like this, and it would have moved like this forever. Makes
Okay,
sense or
sir.
not?
Yes, sir, got it, sir. That's the reason it will try to go always wherever the less heat or less impact.
Exactly. So let's say here particles are less, so there will be less numbers of collisions, so it will go more persistently this direction, this way, right? So that is how the whole thing eventually, let's say eventually after some time, every part you see has exactly same numbers of molecules.
But still, sir, heat will never stop, right? It will still hit, but maybe the impact will be the
It will
less.
still hit, it will still hit, exactly, because they
Okay, sir.
have
With
energy, because they have energy.
yeah, you got it, sir. The previously what I said, with that I was having the concept it will stop at some level, but now I understood it will never stop. Yeah, but it will try to going like average rate, like everywhere it's
Exactly, everywhere.
average.
Now let's say it has homogenized, like every cross section you take, it has everywhere you get equal number of molecules. So doesn't matter which particle was where. Let's say there was a particle here, it got collided and moved to here, right? So that does not mean this part is become less dense, because someone from any other part will travel there.
Then, sir, if you have some time, so I have one more question.
Yes,
See,
sure.
whenever we have the LPG gas, right? So it
LPG gas.
always already the same gas is there, but with because of the pressure, it will become as a liquid. It will turn out into the liquid. But once it will come out to the oxygen level, it will become a gas, right?
Yes,
So
yes,
is
yes.
this a similar concept?
No,
Because
no, 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 no,
maybe
no, 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 no. That is different. That is completely
okay,
different. So LPG with high pressure, it becomes a gas state, and if you sorry, it with liquid state, and with remove of the pressure, sudden removal of the pressure makes it gas again. So
see why I have the question, sir, because the liquid doesn't see in the gas it will hit always with each other, but the liquid doesn't hit. So once it will become a more and more dense, then it changes property from gas to liquid. Then it will never hit. But once it is in the gas form, that will hit.
yes,
So
yes,
because of that only I was
yes, sure, sure, sure.
confused.
But what you are asking, it is the pressure. So you
Pressure.
can you tell me at what temperature uh, and ice melts? What temperature
Uh,
ice it at? 0 degree Celsius?
yes, sir. 0 degree. Water if has a 0 degree more, then it will become ice.
More like there is this called latent heat. You know that?
No, sir.
Okay. So anyway, I'll forget about it. So let's say at 0 degree you have ice. Now it will melt at greater than 0 degree Celsius. Let's say let's talk
That yes, 0 degree. That is 32 Fahrenheit.
Fahrenheit,
Yes.
whatever. Yeah, 32 degree Fahrenheit. This measurement is at at there is a pressure dependence of this value. This is this we are calling at our at a particular height from the sea level.
Okay.
Okay, so if
Okay.
you have you have lower pressure, this melting point changes. I'll give you one pretty good example. So um, what
So that is the
temperature?
reason in the Earth we have the multiple atmospheric layer, right?
Yes,
Because
exactly,
of
exactly,
okay.
exactly.
Yes.
So what temperature water boils?
That 100 degrees.
100 degrees Celsius. Now, do you cook?
Sometimes if no one is there at home, then I will cook, sir.
Okay, so do you know what pressure cooker does?
Yes, sir.
What happens there in pressure cooker? So in inside the pressure cooker, the you don't let the steam go away, so
Yes.
pressure
Yes, sir.
increases. So if
Yes.
the pressure increases, the water in your food boils in less than 100 degrees Celsius.
Yes, sir.
It
Because of
boils,
the pressure. Yes,
yes,
sir.
if the pressure is increasing, it boils less than 100 degrees Celsius, so it cooks faster. So to reach it 100 degrees Celsius, uh, you need more time, more heating. But even before 100 degrees Celsius, it starts cooking. That's why pressure cooker is like, people say no, the gas, it saves gas.
Yes, yes, sir.
That's what pressure cooker is used in. If you go in like hill stations, they have to use pressure cooker for quicker, because the atmospheric pressure is low. So there, the water does not boil at 100. It takes more.
Okay, yes, sir. Correct, sir.
Same thing is happening in the gas cylinder. If you put very high pressure, the LPG gas becomes liquid. The moment you release the pressure, it becomes at the same temperature. There is now no temperature change happening inside the cylinder, right?
Right, sir. So when the knob of the cylinder it will be pressed, right?
Yes.
So because of that pressure only it will come out, but oxygen or the air will never go down, right?
Yes,
Otherwise,
that is the
maybe
that is yeah, that is the valve. Positive pressure to negative pressure. That is a
okay, okay,
different,
okay,
again, that is different physics.
okay.
So
Got it, sir. No,
yeah,
no, no. Got it, sir.
yes,
Got it.
yes, yes. So much is happening. Okay. So yeah, good question. Good that you clarified. Okay, so I was, yeah. So if you are interested enough, look up this thing called Brownian motion of gas, or kinetic theory of gas, if you are interested. If not, then it's fine. So this is how I wanted to end today's lecture. So this is how they are moving. Okay.
Okay, sir.
Okay. So please go through the lectures. There will be really interesting, especially if you, the question you asked at the very beginning of today's lecture, you will have some good motivation if you go through lecture week 1, introduction lectures.
Okay,
He
sir.
has not done anything technical. All he has done there is try to motivate, like why study biophysics, and why, what is the goal of these lectures. Okay.
Okay, sir.
Okay, thank you.
Sir, so next class would be the Monday or Saturday, sir.
Okay, so it's supposed to be on Saturday. It's supposed to
Okay.
be on every Saturday, but this next week, I think this 19th, no, sorry, 17th is the next week. So that one class, I am not sure yet that I will be available on that day or not. If not, I'll try to reschedule it, and I'll inform you guys.
Sir, so if you will be rescheduling it, maybe if you are 17th you are not available, so the next Tuesday you are asked, right? The 20th you are asking for the class, right? Otherwise,
20th.
then your 24th you already have the class.
Yeah, 24th I will be taking class. That's
Oh, okay, got it. So maybe the next class either 17th or either 20th.
yes,
20th. That's
correct,
what, right?
correct.
Okay, got it, sir.
Okay, thank you. Nice meeting you. Keep
Thank you for
if you anything you need.
clarification, sir.
Yes,
Yes.
thank you, and please write if you have any doubts or anything. And if you get
Okay,
any assignment of week 4, please share it with me. Okay.
okay, sir.
Week
Okay, sir.
4, yeah, please. Yeah.
Thank you, sir.
Thank you.
Thanks.
Bye.